Right, so just now we talked about the production of X-ray. So how we actually produce X-ray. This is the X-ray tube. You use it to produce X-ray. First, you heat up the filament wire. Okay, the filament is the cathode. When you heat up the metal, the filament gets hot and then it will release electron through thermionic emission. Then electron travel at high speed. Electron travel at high speed and then they strike the heavy metal. Okay, they strike the heavy metal. Why we need to use heavy metal is because heavy metal means dense metal. So like tungsten, such that their particles are very closely packed. Okay, so when the high-speed electron comes, they will bombard with the metal instead of penetrate through. If you use less dense metal, because particles are further apart, so the high-speed electron come by and then they just penetrate through without bombardment, right? So the reason we use heavy metal is because we want the electron to strike the metal, to bombard the metal, right? Right, so step one, you heat a filament, it produces high-speed electron, and then the electron go and bombard. The keyword is bombard the heavy metal. Now, then three things will happen when the electron bombard the heavy metal, right? Three things will happen. Here, first situation is that let's say this is the heavy metal atom, right? So this is the atom of tungsten. And then you have this high-speed electron coming. These electron, right, when they pass by the atom, because of the electron in the atom of the tungsten, they don't like each other, so they'll try to repel it, they'll try to slow it down or pull it. Okay, so there's forces acting on it, try to slow the electron down. This accelerating electron, okay? This electron that is coming towards it, it will be deflected, it will be slowed down, all right? So when the electron is slowed down, right, the kinetic energy will change. So let's say the kinetic energy of the electron is 100 at first, initial, okay, coming. Then after this atom slow it down, the kinetic energy become 50. Then where is the 50 go? The 50 has to go somewhere, right? So the 50 reduce the kinetic energy that is lost, it will be emitted as photon. So this photon now has an energy of 50. And this photon just happened to be in the X-ray region. So this is an X-ray photon. So how X-ray is produced? This is the first scenario. When electron is slowed down, they release energy, they release photon, they release X-ray. Okay, so keyword when you use to explain how X-ray is produced, you have to mention the acceleration of the electron. They use the word acceleration. It's like electron is being accelerated around the atom of the tungsten. Now, when I say acceleration, it can be acceleration, it can be deceleration. Okay, it can be slowing down as well. Acceleration or deceleration. Right. This is the first scenario. Second scenario is that here's the atom, and then electrons straight away strike the atom and stop completely. Okay, so let's say initial kinetic energy 100. It strike, stop completely, then the kinetic energy turn to 0. In this case, the electron will give up all of its energy. So now the X-ray photon has how much energy? This one has maximum. This is 100 joule of energy. So it gives up all of its kinetic energy. This will also produce X-ray photon. Okay. Now, number 3. Number 3 is that, okay, let me draw again. Here is the atom, and then the electron of the tungsten atom. Yep, come in, guys, just take a seat. Right, so the third situation that it can produce is that electron comes, and then these electron happen to knock off the orbiting electron, right? So you learn about the line spectra, right? The lines energy levels. So let me just represent this in the energy level. You are more familiar with this if I draw it like this, right? So let's say this is the electron here. Let's call this electron 1. This is electron 1. Okay? It is a low energy state electron. And then we have other electron as well, some higher energy electron up here. Now, the accelerating electron, here the accelerating electron comes and bombard with this low energy electron and knock it off this place, knock it off its orbital place. Then that will create a vacancy, like a hole, we say, okay, like an empty space here. That means this accelerated electron, when it hit this low energy electron, they both will leave the atom. Okay, they both leave the atom. So what happened is that now you have created an empty space inside here. And what happened is that whenever there's empty space, the higher energy electron will come down, because they always want to be stable, right? So again, when the high-speed electron knock off the low energy electron, it creates an empty space, and then the high energy one will come down. Once it comes down, de-excites, again you get photon in the X-ray region. Okay? No parking, right? Is it? You park. Double park, huh? Yeah. Did you put your did you put your phone number in the in case, huh? Right. Okay, so now, yeah, I have this session recorded also. Later I'll post it in the evening. So if you miss anything, you just go back. Right. So this is how the three states or three situations where X-ray can be produced. Okay, first is that it will slow down. Second, it hit directly and give up all of its energy. This is like it hit and stop completely. Okay, and the third one is that it knock off the low energy electron, the high one comes down. Okay, all happen in the X-ray tube. Now, see, all the accelerating electron, here we are just talking about one electron having kinetic energy of 100. If you hit the filament, it produces billions and billions of electrons, and all this electron is not moving at the same speed. They have different kinetic energy. So some have 100, some 200, some 1000. So different energy, different range of the kinetic energy. When they slow down, you produce different range of photon energy here. Okay, if the kinetic energy is 200, then you have 150 of photon energy. Okay, the point is that different kinetic energy of electrons, they slow down at different rate and they produce different range of energy of the X-ray photon. That is what gives rise to, we say, a distribution of wavelength. Distribution of wavelength. Because wavelength of what? Wavelength of X-ray. Is like in the graph of wavelength, you will see all different wavelengths of X-ray is produced. This is because electrons, they all have different kinetic energy. They slow down at different rate. They produce different amount of energy of the photon. Okay, so the graph looks like this one down here. So this is a graph of intensity against wavelength. This is like the X-ray produced. The entire profile that you're looking at, this is the range of the wavelength of the X-ray produced. Again, question asks you why there is a continuous distribution like this graph. Then you need to explain how do you explain why there's a continuous distribution of wavelength? First, you have to talk about acceleration keyword, okay? Acceleration, electron, they have different acceleration. They have different kinetic energy, they have different acceleration. Then they produce different energy of photon, and hence different energy of photon give different wavelength. This is like from your formula E equal hc over lambda. So different energy of photon, you have different wavelength. That is where you get a continuous distribution of the wavelength of X-ray. All right. Now, on the y-axis, you see there's this intensity. So intensity again is power over area. Power is energy over time area. So intensity is just how much energy is arriving in 1 second in 1 unit area. So it's like you have 1 unit area, how much photon is reaching in 1 second. So in some sense, I can think of it like the number of photons. The easiest way you look at this graph, avoid any confusion, just treat intensity as the number of photons. So it's like this wavelength, you have this number of photon being produced. This wavelength, you have this number of photon being produced. Okay. Now from the graph, we now know why there is a curve, like a bell curve like this, right? That's the continuous distribution. And then also you see there's these spikes. Why is the spike there and how is the spike produced? Is that the spikes actually come from situation 3. Okay, remember our 3 situations. Continuous distribution is due to case 1. Different electron, they slow down at different rate. Now case 3 says that some electron will knock off the electron and the high energy will de-excite. So because you have specific energy level, right? So when the high energy de-excite, they only give out specific wavelength. That's why you see only specific wavelength has the spike here. This is like when the electron de-excites, they give out specific wavelength. So only specific one you see spiking. Okay, so here and here. So this is due to case number 3. The continuous profile is due to case number 1. Okay, one more very important one is this one here, the minimum wavelength produced. This minimum wavelength, we call it the cutoff wavelength. Now, minimum wavelength correspond to maximum energy. That means this photon is the one that has the maximum energy. Shortest wavelength, okay? How is this produced? Comes back to situation number 2. Remember, there are some electrons that hit and stop on a single collision. This is where they give up all of its energy. So the photon they produce is maximum energy. Okay, is maximum energy and smallest wavelength. So this cutoff wavelength is due to case number 2. Okay, so explain why there's cutoff wavelength. Okay, you say because electron collide and stop in a single collision. Right here, electron collide and stop completely in a single collision. right? So the cutoff wavelength, the spike, and the continuous need to be able to explain all of this. Right, that's the first part. Okay, this is the X-ray, the production of the X-ray. And this device, right? This device is easily heat up, easily heat up. So the copper anode usually first will ground it. You want to ground it because you want to prevent the buildup of negative charge. Once the electron collide with the tungsten atom, okay, where they go? They just accumulate at the copper anode. So you want to ground it. Second is that this tungsten metal, it gets very, very hot, okay, in a very short period of time. When you shoot the electron beam, it will heat up very fast. And this anode is usually spin and then is cool also. It's rotated and cool, okay, to release the heat build up here. The extra high tension EHT is used to accelerate the electrons. Okay, now see, filament and the extra high tension. If I increase, let's say I increase the current at the filament, how does it change the production of the X-ray? If I increase the filament current, that means this one in a short period of time, it will heat up more, and then it will produce more electrons in the same number of time. Okay, so when filament current increase, let's write down somewhere here. Filament current. Okay, the current, I increase the current at the cathode. Increase. That means you have more electrons produced per unit time. Okay, more electron produced per unit time. If you have more electron produced per unit time, one electron, when they reach the heavy metal, that will produce one photon. So if you have more electron, then you have more photons. Number of X-ray photons increase. If number of X-ray photon increase, again, your intensity will increase. Okay, intensity increase. And what happened when intensity increase? How does that affect your X-ray image? Your X-ray image is going to look darker, like this picture down here. This is when I increase the X-ray intensity, or I increase the number of photons reaching the filter. Is the blackening. Huh? So you mentioned increasing the filament current will increase the blackening of the X-ray photon. X-ray image. Okay, now this is number one, increase the filament current and the effect of it. Second, I increase the EHT, the accelerating voltage. Increase accelerating voltage. What is the effect? If you increase accelerating voltage, what's accelerating voltage? This one, the potential difference used to accelerate the electron to bombard with the tungsten. If I increase that one, then electron will have more kinetic energy. And if it has more kinetic energy, every single electron, like if you have billions of electrons, everybody has more kinetic energy. When they have more kinetic energy, then they release more energy of the X-ray photon, this one. Okay, if this one is 1000 minus this one, okay, energy you release of the photon is 950. Okay, so kinetic energy increase, it will increase the energy of the photon being produced. And if it increase the energy of the photon produced, that means more of the photon has shorter wavelength, right? Because if this E is high, the wavelength is low. More of the photon produced, the X-ray, they tend to shift towards the shorter wavelength region. So you can see from this graph, right? This graph, how will it change the graph if I increase the accelerating voltage? If I increase the accelerating voltage, electron has more kinetic energy, so energy of photon is higher, and then the photon has shorter wavelength. Then from the graph, you can see the graph, all of the curve, the whole profile will shift towards the left. Okay, I will show you a graph down here. The effect of number 1 and number 2. If I increase the filament current, the intensity increase, right? So the whole graph will go up if I increase filament current. If I increase accelerating voltage, more shorter wavelength X-ray will be produced. So the graph shift towards the left side, shorter wavelengths. Okay, so the graph looks like this here. The green one. What's the green one? Intensity increase, but the profile is the same. The spikes is the same also. So the green curve shows filament current is increased, but accelerating potential, we constant it. The blue one is when I increase filament, the accelerating potential, but filament current constant. So I produce more shorter wavelength X-ray. Okay, very important, this one. I produce more shorter wavelength X-ray. So why do I want to produce more shorter wavelength X-ray? If the wavelength is short, it's easy to penetrate. If the wavelength is long, it's very hard to penetrate. And if it's very hard to penetrate the human body, then it will be absorbed by the human body. So in some sense, the longer wavelength X-ray is more dangerous to the human body, because the longer wavelength, they cannot penetrate through the body. If they cannot be penetrated, if they cannot penetrate, then they are absorbed. So it's like 100 coming, if only 20 being penetrated, then 80 is being absorbed. If I make the X-ray shorter wavelength, then 100 coming, 80 go through, but only 20 is being absorbed. So I make the wavelength shorter, so it is not dangerous to the human body, not as dangerous as if you have more wavelength X-ray. So you want the graph to shift towards the left side. Okay, so the longer wavelength X-ray, the one that is more dangerous, this is, we call it soft X-rays. You got two types, soft and hard X-ray. And the shorter one is hard X-ray. Short X-ray and hard X-ray. So in the X-ray imaging, we want to increase, we say we want to increase the hardness of the X-ray, because we want to go from this one to this one. We want the first one. We want to increase the hardness such that the body does not absorb too much X-ray. Okay, so that means the blue line here is done by increasing accelerating potential, and the end goal is to increase hardness. Okay, so keyword is hardness. Green one is to increase what again? This one is to increase the blackening, right? Increase blackening of the X-ray. So from the tube, you adjust only two things: filament current or the accelerating potential. Now, from here, what if I change? Okay, we mentioned already what is the effect of changing filament current and the extra high tension. What if we change the metal? Tungsten metal. I change metal. How would it affect the graph? Okay, the graph will like this lah. If you change the metal and you keep the filament current and the accelerating voltage the same, the shape is the same. Okay, the profile is you still get the continuous distribution. You still have the spike, but then the only difference is that the spike is at different places. Because the spike, remember where you get the spike? The spike you get from the de-excitation of the electron in the heavy metal. If you change to different heavy metal, the energy level is different, the de-excitation different. That's why they give out different wavelengths. So the spike position of the spike is at different places. Okay, so you can also say that this is used to tell, just like the line spectra, right? Every single element, they has their unique pattern. Same as this one. Every single one, they have their unique pattern of the X-ray spectrum. Okay, so red one shows both IV constant, current and the voltage constant. The target metal is replaced to another one. Okay, question 1. Example. Give you first. Okay, do number 1. Explain why there is continuous distribution of wavelength. Okay, 3 marks. Mention, if you look at answer sheet, electron have a range of acceleration, first point. Meaning that they are slowed down at different degree. Okay, again, the acceleration here means deceleration lah. They are slowed down and then they release the photon. Number 2, when they are slowed down, the photon are produced. So X-ray photons are produced when the electron are slowed down. So the range of energies give a distribution of wavelength. This one you can say E equals hc over lambda. Explain why there is a sharp cutoff at short wavelength. So that's the minimum wavelength produced, right? So explain why there's the cutoff wavelength, because that is when the electron collide and stop in a single collision. Electrons stop in a single collision. After hitting the first atom, it can hit another one. So there might be multiple collisions. But this one stopped immediately, so you release the max energy, okay? And gives all its energy to one photon. Number 3, a series of peaks superimposed on a continuous distribution of wavelength. So this is due to, so you don't have to say the knock off the electron, something like that. That is just for understanding. The way you answer, you just say the electron de-excites. Okay, the excitation of orbital electrons. The excitation of orbital electrons in target metal. Right. In the X-ray imaging of the body structures, longer wavelengths are frequently filtered out. How the filtering is achieved? Now, just now we mentioned the increased hardness, right? So from, let me go back to this one. From just now, we increase the accelerating voltage to increase the hardness. That's one way. Yeah? Second way you can increase the hardness is by using a filter. You put it at the window here. Like when the X-ray is coming out, it passes through this filter. This filter, we use aluminum filter. The function is to absorb the longer wavelength X-rays. instead of the body absorbing it. Okay, so coming out here is like, if you look at the spectrum, let's say this is my spectrum that is being all the X-ray being released. If I put a filter, let's say I filter out over here. I draw a line here, and let's say I filter out over here. So all the longer wavelength is absorbed by the aluminium. Then only this part, the shorter wavelength one, is coming out of the tube. And this will go to the body. Okay, so if without the filter, then this part will be absorbed by the body. So that is another way you increase the hardness of the X-rays. Right, so we say filtering is achieved. Aluminium filter. Use aluminium filter. So it will absorb instead of the body absorbing. Suggest the reason for this filtering. Do you mention long wavelength is not absorbed by the human body. So that long wavelength is not absorbed by human body. So the long wavelength is like the soft X-rays. Okay, so the first part is on the producing X-rays. And what about the detection, like the formation of the images? How the X-ray is formed? You stand here, let's say you stand under the sun. The sunlight goes here, you block the sunlight, and then you see your shadow here. But then the shadow, you see the shape, you cannot see what's inside. It's all like same intensity, we say. Same shape, same blackness. Because your body block all the lights. No light can go through. It block all the lights. That's why no light shine on the background. It's all black. In the X-ray, right, it's very simple. It's very similar to this one. Okay, very similar. Just that you stand here. They shoot the X-ray. But your body doesn't block all the X-ray. Not like the sunlight. Your body, you got tissue, you got bone, you got, okay, water. They block X-ray to a certain degree. Okay, they absorb X-ray to a certain degree. Is different. Every tissue, cells, the water is different. So as a result, you get more of the X-ray coming out here, less X-ray come out here, very little X-ray coming out here, different intensity over here, here. So it forms the picture here with a different intensity of blackness. That's how you see what's inside. Okay, that's why the bone appears to be clearer, because the bone block all the X-ray, but then the body tissues allow some of it to go through. So you can kind of see the shape of the image, or the scale. We call it a gray scale. It's like some very black, some gray, less black. It's because of the intensity. Okay, that causes that produces the X-ray image. If the X-ray block everything, then you just see the shadow. You cannot see what's inside, right? So on the basis of the production of X-ray image is the absorption of X-ray. So we will say the absorption. Okay, so essentially X-ray is produced by absorption. And in absorption, we have a second term We call it attenuation. Okay, attenuation is absorption of X-rays. Right. Now, X-ray is electromagnetic, right? So all electromagnetic waves, when they strike a surface or a boundary, let's say we have a boundary here. What is a boundary again? Separate. It is a line that separates the two medium. You have medium 1, medium 2. So medium 2 can be like, okay, let's say human body tissue. Medium 1 is air. X-ray is coming from air. Okay, when the electromagnetic ray strikes the boundary, 3 things will happen. Here I always mention, what are the 3 things? Red, reflection, absorption, and transmission. Okay, the transmission of X-ray. So here 100 strikes, 60%, okay, let's say 10% reflected, 90% go in. Maybe 10 is absorbed again. 10 is absorbed in the boundary, so left only 80 that is being transmitted through it. Okay, now during the transmission, here is what we are, our focus is during the transmission. Okay, our focus is during the transmission. During the transmission, is this energy is going to maintain 80 as it travel in the medium number 2. We don't look at reflection and absorption. Huh? Okay, this is reflection. This is absorption. That is the transmitted one. Focus on the transmitting one, 80. And during the transmission, this 80 will lose energy. All right, it will lose energy. And the way I draw is like this. Here you have X-ray coming. How they lose energy is that they will lose energy exponentially, like this. Okay, so you have seen, you have learned damping, just like damping. Here is your X-ray. When it enters the medium, traveling in the medium, then very fast, the energy decrease like this in a exponential manner. Right, so this is the 80. So you start with 80 here, not outside, is the one that just entered 80% of the energy, and then it goes through this exponential decrease, the damping. And the damping inside this medium is attenuation. Okay, so attenuation is basically mean damping. Damping of the X-ray as it travel through a medium. Any medium, there will be attenuation. So by the time it reach here, maybe left, okay, 40. So half energy is gone. So come back to exponential. We mentioned about exponential again. So it has to do with the decay stuff. So like I said yesterday, the decay equation, it can be applied everywhere. Population, customers, the bacteria multiplying, all of that. Even here, attenuation of X-ray, we can apply the decay equation. Anything that is exponential, so I will write I, we will use intensity in this case. What is the intensity? Initial, I naught. And what is the intensity? Somewhere down the distance, I. It's like how far you travel in the medium already. It is measured in X lah. In X. So let's say like this is the boundary. So you're going this far, measure in X, somewhere down the medium. What is your I compared with the one that is entering here, I naught? Okay, so from here to here is an exponential decrease. So I will write I equals I naught E minus what? Minus a constant, we put a mu X. Now, here, if you compare to your decay equation, your decay equation is, can be activity A naught E minus lambda T. This is your decay equation, or the number of particles. N naught E minus lambda T. Lambda, recalling back, is the probability of decay. What is this? Compare this one. Mu, we call it the attenuation of the medium. It is the, you can think of it like how much it is causing the damping. How much is the medium? How much damping is the medium causing? Okay. In the decay one, is like the chances of decay. But in this case, the mu is how much damping the medium is causing. That means if large mu, the damping is very large. So the decrease in energy is very fast. And x is the distance lah. So as the distance increases, this one keeps decrease the intensity. Okay, of the X-ray. Now, one thing to note also that the X-ray is striking the boundary. They must be parallel to be able to use this equation. They must be parallel ray. Why they must be parallel ray? Because you are talking about intensity here. Intensity is power over area. If your ray is like spreading like this, then your intensity will change. Over here, point A compared to point B here, the intensity will be different already because your area is changing. So you have to make sure that the ray incident on the boundary is parallel. Then we can apply this one over here. Okay, so the attenuation coefficient, this one, the mu, linear attenuation coefficient is different for different parts of the body. So it's like bone, muscle, the brain, okay, the blood, they have different values. So depending on, let's say the bone is about 0.528, muscle 0.237. The higher the value, the more the absorption. So bone is, of course, the highest one, 0.5. Okay, the higher it is, the more the absorption of the X-ray. Okay, what about the unit? The unit of the coefficient, same as the unit of the X here. If the X here, they use meter, then here I will use meter minus 1. So when they multiply, they got cancelled out the unit, okay? If this one is millimeter, then mu you will use millimeter. When you use the equation in calculation, be careful with the unit. The mu unit and the X unit, you want to make sure they are the same. Huh? Okay, so using this one, here's how the X-ray is produced. So the X-ray comes, different parts of the body, the bone, the muscle, they have different linear attenuation coefficient. So when the X-ray goes through your body, different damping occurs, right? Because different coefficient. So coming out from your back, the intensity is different already. You can calculate it using this equation, I. Coming out from the back, from your back. Here you have I1, I2, I3. They all reach the film. There's chemical reaction there. They produce the blackness, different intensity of blackness. Okay. Question 2. Two reasons other than absorption why the intensity is different other than absorption. You have reflection. So talk about reflection. Talk about the source is a point source. So the ray is like spreading. So it's going to be different intensity again. So we said non-parallel beam. And also due to reflection. Okay. Diffraction, scattering, okay, it will all that will occur. Right. B. Right, this one you incident the X-ray through the, okay, one is through the muscle only, another one is muscle and bone. Thickness all given, linear attenuation all given, bone muscle. Calculate the ratio, intensity of X-ray beam incident on specimen. Okay, meaning that this one, okay, let's call it I naught. I naught over intensity of X-ray beam emerging from the specimen, emerging I here, coming out of the back. Okay, I naught over I. You want to get this ratio for the beam passing through the 4 cm thickness of the muscle alone. All right, so we do the calculations. One is for only the muscle alone. So for the muscle alone, then we do I equals to I naught E minus mu X. Okay, the ratio, so you just bring this one over here, I over I naught equals to E minus mu X. Since it's just one medium, right? You only pass through the muscle. So this one is 0.27. And then what's the unit? Be careful with the unit. This one is in cm minus 1. And then look at your X. 4 cm. Okay, same unit. 4 cm. And then they want I naught over I. I just flip this one. I naught over I. E 0.27 times 4. Like this. Equals to 2.94. Okay, number 2, the bone and the muscle, right? This one you got 2, so the X-ray pass through 2 medium. It goes through the muscle, then bone, then muscle. Right, just to make this easier, I will combine this chunk with this chunk. So I have, let me redraw this one. I get something like this. It passed through the muscle, first 2 layers, and then the bone. Doesn't matter which one comes first, okay? As long as they add up to this one. Right, so you have I naught coming in, coming out of the muscle here, let's call it I1. Okay, then I1 go through bone again, coming out here, you have I2. We separate it because you have 2 different medium. Okay, length, this one muscle is 4, you minus the bone 1.5, so this is 2.5 cm. And then this one is 1.5 cm. Okay. First one, let me write it here. I, for the muscle one, I1 equals I naught E minus mu X. Right? Because I1 is the one coming out. And then I naught is the incident go through it. So I1 equals to I naught E minus mu X. I1 equals to I naught. This is minus 0.27, 2.5. Let's put this aside. And for the bone, we get I2, the one emerging, over the incident bone. The incident bone is, okay, I2 equal I1. E minus mu. What's the mu of the bone? Mu is 3 and then 1.5. Okay, then we put this one, put it inside, put it inside here. I2 is, this one become I naught E minus 0.27, 2.5, and then times E minus 3 and 1.5 like this. Okay, so this whole thing is the one that I substitute inside here. It's actually the emerging of the muscle. That is the incident of the bone. The one that comes out from the muscle is the incident to the bone. So I sub inside here, then I will get I2 over I0 equals to, okay, then we calculate this one. 5.656. Again, we flip it. 177. Okay, so answer is 177. For this is for 2, number 2. Now the 2, it says using your answer in 1, suggest and explain whether X-ray image of this specimen is likely to have good contrast. Okay, so from here, from only the muscle one, our fraction is 2.94. And from here with the bone, our fraction is 177. Again, what does this value mean? You look back at what you're calculating is a fraction of the emerging over the incident. It's like when you have 100% incident, like how much of that coming out? So this number is a fraction. Okay, a percentage of that going through or transmitted. Same here, we have I2 over I0. Okay, a percentage of that being coming up. Oh, sorry. This one is the fraction being absorbed. Because this is absorption, the attenuation is absorption when it goes through the medium. Okay. So how do you know whether it has high contrast, good contrast or not? If the difference is very big, then the contrast is good. What is contrast? Contrast is like the difference between the black and white. The black gets blacker, the white gets whiter. So the difference is big. That is a good contrast. So if your value is large, far from each other, okay, the difference is big, then you have a good contrast. So you mentioned good contrast. Why? Because each ratio is very different. Okay, the ratios are very different. Okay, the ratio is a measure of transmission ratios. Okay, number 2, if you have finished, 3, 4, 5, and 6. Examine the movie. Next week, final week. Number 3, the ratio of the intensity is also ratio of powers. Calculate the ratio in decibel. So if you want to get in decibel, you have a formula for the decibel, right? dB is equals to 10 log I over I naught. Okay, so intensity at a certain point with respect to intensity of the source, I naught is the I. We can use the fraction from the fraction you get in number 1. The 0.81. Okay, so 0.81, this is the ratio of what? The ratio of I1 and over here, right? The transmitted ratio, the transmitted intensity over here and over here. So if they want the scale in this decibel, then we'll put 10 log 0.81. Here we get minus 0.92 dB. Notice that in the log scale, if the fraction is more than 1, the log will be a positive values. It's like you log anything more than 1, it will be a positive values. Positive simply means in the log scale, if you get a positive, that means your numerator, okay, your transmitted intensity is larger than the initial intensity. If you get a positive in the log scale, like in the decibel ratio, But here you see I get a negative in my ratio. Negative means my fraction inside is less than 1. You log anything less than 1, you get a negative value, which also means that the transmitted intensity is less than the original one. So it's just they want to put it in the log scale, nothing really special about this one. Okay, they just want you to express the ratio in the log scale. Okay, question 4, you want to give the difference between CT scan and X-ray. What is CT scan? Okay. X-ray is you just take a 2D image. But CT scan is 3D, but then how do you get the 3D image of X-ray? I think I have a short video here. Let's watch a short video on the CT scan. This one. Okay, so you see how they take the image, the X-ray image of a 3-dimensional. Why you want to take 3-dimensional X-ray? If you say like the bones, like your finger bones, all that we don't need to take 3D lah. It's just 2D is enough to analyze it, to look at the pictures. But if you are talking about like the pelvic, hips, okay, all this, the brain, the skull, all these bones is like more rounded shape, like ball shape. So you need view from different angle, okay, to see if there's like cancerous tumor, okay, it could be any reason lah. You want to take the CT scan. It's mentioned in the video. So it provides like a more 3-dimensional visual lah for the CT scan. It's basically the same as X-ray, it's just 3-dimensional. Okay, so you look at like how they take the image of the 3D X-ray.
A CT scan, also known as a CAT scan or computer.
Let me turn on my volume.
A CT scan, also known as a CAT scan or computerized axial tomography, is a painless diagnostic test that uses X-rays and computers to create cross-sectional images of bones and tissues inside your body. Your doctor may recommend a CT scan to examine your body for any of the following: blood clots, broken bones, cancerous tumors, infections, internal injuries and bleeding, and signs of heart and vascular disease. A CT scan helps your doctor select the correct location for surgery, biopsy, or radiation therapy, check the treatment of cancer or heart disease, and check your condition after surgery. A CT scanner is a large square or round X-ray machine with a tunnel through the center. During your CT scan, you will lie on a table that slowly passes through the tunnel. As you move through the tunnel, a giant ring called a gantry will rotate around your body. The gantry contains a tube that will release X-ray beams and detectors that will measure the amount of radiation absorbed by your body. The X-ray beams will capture many views of your body from different angles as the gantry spins. The detectors will send data to a computer that will create cross-sectional images of the bones and soft tissues inside your body. The scan allows your doctor to see the location of a condition inside your body, which will help them decide how to treat it or to see how well your treatment is progressing. In some cases, you may receive contrast dye before your procedure in a drink, an injection, or a barium enema to make it easier for your doctor to see certain areas of your body. If you received a drink with contrast dye, your esophagus or stomach will be highlighted. If you received an injection, your blood vessels, gallbladder, liver, or urinary tract will be highlighted. If you received a barium enema, your large intestine will be highlighted. After the procedure, you can resume your normal activities. If you received contrast dye, drink plenty of fluids to help your kidneys remove the dye from your body.
Okay, you can see how they take the image.
The gantry contains a tube that will release X-ray beams and detectors that will measure the amount of radiation.
This one, they just take one slice, like one slice of it. It's like, okay, let me see if I can draw it. It will rotate at different angles.
Absorbed by your body. The X-ray beams will capture many views of your body.
Okay, why it needs to rotate? Because if it stays at one side, right? Let's say it stays here, and then the X-ray comes through, like comes to the skin here, right? And some X-ray might be blocked by, let's say you have like bone here, then it will block the X-ray that it cannot detect on the other side. That's why the X-ray has to spin to the other angle. So it takes from this side, from this side, from this side also. So every single angle for just one slice. Like one slice means, because this thing, it will push it in, right, into the tunnel. Once it goes in, then you take like the second slice, the third slice, the fourth slice, like this, right? So sometimes you'll have like more X-ray tube over here. It's like just instead of just one, right? They put 2 or 3 so that they all work together, and then you can detect like a kind of like a frame by frame image of the beating heart. Okay, because the beating heart is very fast, so one is not enough. They need 2 at the same time, like that. So they can produce like 2 images in 1 second. Okay, so basically it's like this one. Let me go back to the note. Here, okay, the pelvic bone, the hip area. Okay, this is where you need CT scan to see it. And the way it works is like this. What I mean by one slice is like this one. If I draw here, okay, this is the, let's say you're scanning this one lah. You're scanning this one, and here you're just scanning one slice. So if I draw here, only this slice that you're scanning from different angle. So you have the detector over here, sorry, the X-ray tube over here. You scan only this slice, and once it rotates over here, again, it only scans this slice. And when this moves, here it moves left and right, okay? Once it moves, then you scan the next slice. Okay, it's like every single slice, they record the image. So what you see in this picture here, you see very like similar pictures, right? Okay, let's say this one. This is the picture of the brain, of the human head. From the bottom picture, the first one, this is like starting from the top. It's like you scan the top slice and then go to the next one, the next one, the next one. Is like you're going down from top to here, okay, to the chin. So every single image is like you go from one slice to the other, to the other, to the other. Okay, so it's like a cross-sectional view, a cross-sectional view. So they combine every single slice, of the image, and then they form a 3D image of the human head. Okay, same as this one. I take every single slice, the next one, then I can form the entire solid. It's kind of like a 3D printing. Like the 3D printing is like they build one layer by one layer by one layer, and then overall you get the whole thing. Okay, this is what the CT scan is doing. Is by taking many 2D images and then make it into 3D by using computer. All right. The word CT, computerized. C. That means you need computer to help you process the image. Okay. So the good thing about this is you can adjust which part you want to look at. Which part you want to look at. Okay, I want to look at over here, or I want to look at over here. This slice, I want to focus on this slice or this slice. This allows the doctor to find, okay, where is the cancer cell of that. Okay. Yep, that's why you see this image, like all image looks kind of similar. It's because they are taking slices, very, very few slices of images. Right, so the CT scan and the X-ray, the questions, how they will ask, okay, questions like distinguish the difference between them. Okay, first you have to talk about one is 2D, X-ray and CT scan. One is 2-dimensional, one is 3-dimensional. How do you get 3-dimensional? By taking multiple 2-dimensional pictures. So I would say the CT scan consists of many X-ray images of a slice. Other differences, such as the exposure. X-ray is just, okay, this one has less exposure. This one has more exposure. Usually they don't recommend, the doctor will not recommend CT scan unless you have like critical conditions, because the exposure is so much higher. You're not taking just one slice, you're taking multiple. So you're exposed to the high dosage of X-rays. Okay, what else? I think that's it. You can also say there's no depth in the image for the X-ray. No depth. So it's kind of just 2D, one plane. There's no depth. CT scan, okay, image can also be rotated. One more, last one. Image can be rotated, can be seen at different angle. Okay, you can see in the marking scheme, it's all in the marking scheme.